Good afternoon, all. So, welcome to the technical seminar on the new insights into the concrete contamination by persistent fluorochemicals from Firefighting Foams, which is co-organized by the Hong Kong Polytechnic University and also the HKIE Civil Division. So this afternoon, we are honored to have Professor Liu from the Department of Civil and Environmental Engineering of PolyU to give us the webinar on this title. And Professor Liu joined the CEE at PolyU in July 2024 after serving as an associate professor in McGill University in Canada. She leads a research program focused on mitigating the environmental and health impacts of emerging organic pollutants, particularly PFAS. Her work integrates studies on PFAS, environmental fate, behavior treatment, and mitigation through laboratory experiments and fieldwork. And her current research also explores PFAS in consumer products, fluoropolymers, and novel fluorochemicals used in lithium-ion batteries. She actively collaborates with government agencies and private industries to address soil and water pollution challenges. He has acted as a scientific expert for law firms in the US, Canada, and Australia on PFAS-related lawsuits and litigations. So it is time to give the stage to Professor Liu. And before that, if you have any question during the webinar, you are feel free to type in the boxes, and maybe we can address all of them after Professor Liu's sharing. So let's give our time to Professor Liu. Thank you.
All right, thank you, Daniel. Thank you for the invitation. Good afternoon. Welcome to this seminar series. I'm just so glad to see so many people online at this time of the day. I'm just going to quickly introduce the department. I'm sure you know about it. So PolyU's CE department is globally recognized for its excellence in research, innovation, and education. So several programs consistently rank among the top ones worldwide. And many scholars in the department has been ranked as world's top 2 scientists over the years. Actually, my photo should be there as well. So one year I made it to the top 2%. So here are a few examples of major grants recently awarded to our professors, focusing on topics such as infrastructure, air pollution, transportation, and public health. You probably recognize a few familiar names here. Let me see this one. So Professor Teng Jingguang is the university president, and Professor Xiangzhong Li, he is current dean of the Faculty of Engineering. A few more examples of major achievements, such as of colleagues Professor Ben Liu and Professor C.S. Peng. C.S. Peng, he's the head of the department. So they recently received the Green Tech Fund and Lantau Conservation Fund. You probably know these funds. These are really intended for promote green innovation, supporting a low carbon transition, and protecting biodiversity in Hong Kong, so ensuring a more sustainable future for the city. A few more examples, guess for professors, these are really important thing to talk about. These are just the RGC Collaborative Research Fund and Research Impact Fund. So these are for interdisciplinary projects. So again, these funds enable research in areas such as sustainable construction materials, innovative solution for urban resilience and climate change adaptations. Our academic program covers undergrad degrees in civil engineering and environmental engineering. We also have 2 different streams of postgraduate programs. One is for course-based, only these top programs, also in civil and environmental management area. We also have a research program that's really strong. So again, these program prepare students at different level to tackle new challenges in infrastructure, sustainability, and environmental management. So PolyU has nurtured, and also CE nurtured many exceptional alumni who have taken on prominent leadership positions in both public and private sectors in Hong Kong. I'm sure some of names displayed here are familiar to you. So these are from CEE. So currently, the department is equipped with 30 state-of-art laboratories, 2 workshops, mechanical and electronic, and 1 research center in Shenzhen, Guangdong Province. These provide robust support for both research and teaching activities. How to connect with us? I'm sure you can search for us, but here are the barcodes for the QR code for different social media channels. And we also have newsletters that we share with our alumni and people who are interested in our program and department. So I'm going to put up this slide later after I finish my talk. So I'll go right into my topic. Because I'm new here, so what I'm going to talk about really from my research conducted back in Canada and US. So I've been in Canada for 12 years, and a lot of my work focus on these persistent chemicals. Just kind of a little bit warning. So my talk is a bit chemistry heavy. So because when you talk about organic pollution, there's no way to get around chemistry. And for these chemicals, we call them PFAS. These are probably the most chemistry heavy contaminants that people have ever worked on. So apologize ahead of time if you find it too chemistry heavy, but I'm sure there are some things even you don't have a strong chemistry background, you can relate to your daily life. So these are man-made chemicals. They don't exist naturally, and they actually were invented in 1930s. So to understand PFAS, we have to start with basic organic chemistry. So I put up the slide for kind of for most of my academic talks. And if you find it's too much, and but I want to just show you something. It's maybe things is not as complicated as you think. For instance, this number 8 chemical is the name is called PFOS. So by the end of the talk, if you know not much about PFAS, and you can Google, and you're going to find so many articles and news story about these chemicals. But so I won't put you through too much of this, but this is kind of the daily challenge my students and I deal with, navigating the complex world of PFAS chemicals. So let's just break down the makeup of these chemical structures. So here I put a name called a legacy, because later I'm going to talk a little bit about the evolution, how we're going to classify these chemicals and which one are, should we study and which one has been studied. So a typical molecule has 2 parts. This blue part, we call it perfluoroalkylated chain. So right now, the structure I'm showing has 8 carbon. But the carbon chain can be very short and can be very long. So general range is the 3 to 16, but people actually found as short as 1 carbon, as long as 20 carbons. And the R is called hydrophilic functional group. So a lot of these chemical are surfactants. So they have hydrophobic tail, the blue one, the hydrophilic functional group. And the R has many, many variations as well. So how do you think about this one? So actually, the chemical industry managed to create so many different chemical structures, almost like the way we build Legos, right? So you get your basic Lego building blocks that might not have a lot of different shapes, but when you mix and match them with different colors and quantity, you can create, millions of different structures and million different things. So it's the same thing with making, chemical as well, especially for PFAS. So 2 names I'm going to keep mentioning a lot is the PFOS and PFOA. One is 8 carbon, the other is 7 carbon. One has sulfonate, the other have carboxylate group. These are the most studied PFAS chemical structure out there. A little bit of timeline. So the chemical were invented in the 1930s. From 1950, they were commercialized. So we've been using them for a long, long time. Of course, in recent years, their production use has been increasing because of the economic development. Really, the most important time point is between 2000 2002. That was a time actually 3M, one of the biggest manufacturer of these chemicals, actually stopped making PFOS and PFOS related products. That's even before most people realize there's such a thing called PFOS or PFAS. That's because in the 1990s, when they have better tools, they start to notice there are a lot of health problems with their workers in the occupational exposure scenarios. And then they decide, and later on they did a few studies, they found actually these chemicals are detected worldwide in drinking water in the Arctic and in polar bear, and they decided not to produce them anymore. But that's actually the start of the research on these chemicals. Another important one is called PFOA. So PFOS was made only by one manufacturer, 3M. PFOA is a much more common chemistry made by almost most of other chemical manufacturer. It's because that time PFOA was still used to making a lot of polymers. We familiar with the Teflon type of polymers. They have to find replacements. So PFOA has to be used for a little bit longer before they can find replacement. So it took another 15 years for the industry kind of phase out both two chemicals. But that's like saying that this is just the start of the story. This is just a different view of what PFAS are. So this evolving attention to particular type of chemicals does not really reflect their emergence of timelines used in industry, because early times, there's a lot of information just not available. These are a lot of chemical information. This is just not only applied to PFAS, but a lot of chemicals we use in our daily life. Industry can mark them kind of as confidential commercial information or confidential business information. Government agencies know about them. They are actually not obligated to review the chemical structural nature of it. So we actually been just a lot of time we don't know we're using. So early time people thought, oh, PFAS is just too chemical. Later on, there's more, and then they found there's more, and they all have these funny names, and now this is where our stage is at. We want to focus as many PFAS as possible because of the analytical tools we have. A lot of now we have AI, and we try to be very comprehensive so that we want to use these chemicals in a much more responsible and sustainable way. So, what are PFAS? So these structures all have multiple fluorines, right? So if you have a little organic chemistry background, you know that these are very stable structures. So they're thermally stable, they're chemically stable, and then they give them very important unique property. That's why we use them a lot, but we don't usually use them in huge quantity because these are quite expensive chemicals. So if you have, nice Gore-Tex clothing, outdoor gears, they have this nice coating that waterproof, oil-proof, and then they very likely they contain PFAS. And there's nice cosmetics. These are, if they have cosmetic, not only the lipstick, but the mascara. If they actually don't smudge easily, they really are among the best cosmetics. There's a very high chance they contain PFAS. And then today I'm going to talk about firefighting foams. So I'll keep this topic, but also you all have, non-stick cookware, right? These are coated with fluorinated polymers. And then there's many, many other products out there. If their performance is superior, there's a very high chance they contain PFAS. So here I'm listing the 12 top producer in the world. So I actually worked at DuPont company for a while, and my PhD project was actually funded by DuPont. I was working on this chemical for quite a while. So top producer only, I think one of them is from China, but there's the other ones are from North America, from Europe. So DuPont later on sold their kind of business to form a spin-up, a newcomer kind of Chemours, but it's the former DuPont company. Again, there's a lot of things happening since then. I think PFAS is among the chemicals there's been through a lot of change over the years. If you want to know a bit more, you want to know authoritative kind of information exactly, not just only the news story, you can look up at OECD website, and they have these reports about what are PFAS, how they're used in food packaging material, how they're used in different paints and varnishes, or, they're used in polymers. So on the right, I'm showing the complexity of this chemical, but this is just a start, okay? These are just a start because this is structure more or less similar to what I've shown you. So people have been studying this chemical for about 20 years. However, in terms of volume or mass or quantity, most products actually made into polymers. So polymers in general, they're much more stable. They are not as toxic because everything else in these are tend to be like we call smaller molecules. So smaller molecules are very, very mobile. They actually absorb more easily by living creatures. So but polymers, when you digest polymers, if they're large enough, they actually usually don't get into bloodstream unless they're tiny, like nanoplastic size. But that's a different topic. That's also kind of hot topic these days. Anyhow, so polymers, should we keep using them? Well, I think the industry, obviously, yes, we do need them because without these fluoropolymer, we won't have our cell phones. Also, I think Daniel introduced you about my background. Right now, one of my focus is to looking at PFAS in batteries, right? Lithium-ion batteries, sodium-ion batteries, they all need a lot of fluorochemicals to make them function. So I'm gonna talk about firefighting foams. The kind of the correct name is called AFFF, aqueous fume forming foams, or some people called aqueous firefighting foams, but AFFF is its official name here. The way you think about these foams, they are used for a Class B fire. So any time there's a flammable liquid fire, that means gasoline, right? That means that the best firefighting agents are these PFAS containing firefighting foams. In US military, this is actually mandated. They actually have to use it. Right now, the landscape is changing. That they are in the transition into a PFAS-free, but in a lot of critical application, for instance, I know in oil refineries in part of China, they still think there's no better replacement. They have to use PFAS containing firefighting foam because they're superior performance. The way you think about these firefighting foams is the way I would think about like liquid laundry detergent. They have very similar color. They're usually a little bit light brownish and a little bit kind of sticky, all right? They have that kind of very similar to our detergent. The way you use it is you actually mix with water with certain percentage, like dilute like 30 times or 20 times, and then you create these foams and you use the foam to fire to fight fires. So the practice started like from 1967. This is U.S. military because they had a disaster at that time. They found they were not ready to combat big fire. So that time they kind of mandate to start using AFFF. Since then, for 3 decades, they've been using they kind of dispose them kind of very without a lot of treatment. They flush into groundwater, surface water, soil. And until the past, 15, 20 years, we realized these are really not supposed to be chemical. They just kind of release into environment because they're very persistent. So contamination have been found worldwide in places where firefighting foams use, also for other type of industry. There's just so many studies on the appearance of these chemicals in the environment, also in humans. So I'll talk about that in a minute. So this is just to give you just a snapshot of what I did in Canada. So a part of my past research focused on environmental monitoring. For instance, we've been looking at soil. There's a twin derailment accident. So after the accident, put out fire, these are PFAS containing firefighting foams. And this we did with Transport Canada. So this is in airports, in Canadian airports. And this is a survey we did in Quebec drinking water. So of course, level in drinking water is low, but still you can detect 24 classes PFAS, about 50 of them in drinking water, even though they're a trace amount, but they are in drinking water as well. So why do we care about them? Because they are widespread present. So study done in the US found PFAS detected in blood of 97 Americans, but that was a number I think was done quite a number of years ago. So that's when they weren't focused as many PFAS. I think the study was done today. I'm sure the number probably may be higher, maybe 99%. It's a very prevalent. So probably most of us also have some trace amount of PFAS in our body because they're just floating around everywhere globally. There's many opportunity for human exposure, and they're very persistent. They don't mineralize, so they just like the way they actually almost like metal, right? They're just very hard to destruct them. The one issue with them is they're bioaccumulate. We don't know a lot of toxicity of a lot of these compounds, but they bioaccumulate in humans. So these 3 compounds we listed in human. Once you get into your body, it takes about 3 to up to 10 years for 50% of them to actually get excreted out of your body. So somehow they just keep circulating in your human bodies for one reason or another. And then some of them, so I have to emphasize only some of them has been confirmed has chronic health effect. These also limited to a very few number, PFAS, PFOA, and right now this is called PFHXS. It's like the longer chain, shorter chain, so they're very similar. So these are 6 health effects has been confirmed, and there's more study out there. So I only provide the most authoritative information from US CDC. There's new kind of health reports. Those are in the kind of literature. If they haven't made in the public kind of government publication, I won't usually talk too much of them because they haven't been fully kind of validated. But to be just to let you know that not every PFAS is toxic. A lot of them because we just don't know how toxic they are. Here, just want to mention a bit more. Is recently there's just we start to pay attention, and the OECD is kind of a nonprofit organization in Europe. They want to kind of future proof, so how many PFAS are there? And they actually expanded the definition of PFAS. So on the left is the definition in the past. So mostly these long chain structures, but they expanded to include things as long as one carbon has like structure like this. So I'm going to put in here, or have some structure like that. Even though it has this aromatic structure, they still call them PFAS. So what's the implication of expanding the definition? So here is the implication. So this is a public available database, and people are actually still trying to kind of to dig out all the chemical database out there, see if we go by the OECD new definition, how many PFAS are there? So this number right now is over 6.5 million. So it doesn't mean the 6.5 individual chemicals, but because there are mixtures, you can have things that kind of double counted, triple counted, depends if it's in single chemical or in some kind of formulation. But just comes way too many chemicals that were not traditionally studied by people in this field, also include chemicals that were never used, right? Because there's always synthetic chemists and they create so many different things and just put in a database. Doesn't mean they're used. But this database also say regulatory, we are looking at 26,000 chemicals. Still, it's still pretty large number, right? So right now, I think for the things we can manage a little bit more easily is maybe these numbers, a few hundred of them. So there's just a lot of things we're still trying to understand. For me, I personally don't like this definition because I think their intention is really to make it future-proof. Try to unify criteria so that we have a little bit global policy that's aligned. So not one country does one thing, the other country does something different. But for me, it's really just including a lot of problematic chemicals and diluting the focus on high-risk chemicals. Also create a lot of weak boundaries because some country may not agree with the OECD definition. For instance, USA, they have their own kind of definition and kind of done by US EPA. Anyhow, so this is just my take. So a lot of people say PFAS are toxic, which is not correct because most of the toxicity actually is unknown, right? We only know the toxicity of a few selected chemicals. How about regulation? So I'm gonna so this is borrowed from a consulting firm Arcadius. The 1 year they have a nice summary of what's out there in terms of regulation. So US EPA is going to regulate what they are actually starting to regulate drinking water of PFAS it's going to take 5 years to implement because right now it's just prepare for the municipality for different states to prepare it for it. So you see how low the drinking water regulation is. 4 nanogram per liter, such a low level, right? They actually regulate 6 of them. They have their, you can read all the details out there, but we're talking about regulate very, very trace level of chemicals. In Canada, it's slightly different approach. So as we talk about in any water sample you get, if you detect PFAS, it's very likely not a single one. So Canada decided to regulate based on a sum of 18 PFAS and based on what we can detect and target the 30 nanogram per liter. Right now it's a draft. It has not been fully implemented. Just telling you that it's in a way it's a very conservative approach is how they regulate. So because of these no numbers, right, that's where we start to looking for all the potential sources. Because even though the absolute mass of certain sources is not significant, if they get into the water and they are going to be very likely going to exceed drinking water limits in some places. So why we compare concern of PFAS in concrete, I'm going to speed up a little bit. So this is really from 2015. This is because these firefighting foams used a lot in airports, military bases, fire training ground. There's just always a lot of opportunity, PFAS actually are sprayed onto concrete. So remediation or focus in the past is always on soil, surface water, drinking water. But people didn't really pay attention to concrete because they never thought that PFAS can be trapped into concrete. And then now they actually did the study 2015, and then they actually found in the site when they actually remove all the contaminated soil, try to remediate the groundwater. Every time they rain, they see a pulse of high-level PFAS in the groundwater, and they actually trace back to a concrete called firefighting pads. So these are structure usually you see in these places, right? You see the structure burning on concrete, and that's how they train firefighters. So what is concrete? I'm sure you know what is concrete, right? Composite material made of aggregate, like sand, aggregates of sand bound together by cement, right? These are the most used construction material worldwide. So they are porous. So right now I'm showing structure. The blue dots shows the pores. They are porous. They can absorb water, but pores are not continuously connected. That's very different from soil, right? For soil, they have path. For concrete, the new one, they shouldn't have the connected path, but water can slowly diffuse through. But there are cracks, right? Once you crack, water can get in a bit more easily. So contamination concrete by chemicals mainly studied using chloride because chloride ingress has been studied because of its impact on concrete strength and durabilities. So from 1915, so this is really the first evidence. What you see here is a concrete training pad. On top of these are numbers of nanogram per gram, very low number of PFOS, PFOS, and some of like 15 PFAS together. You see the numbers are not huge, but again, when you add it up together, the mass loading of that one concrete pad is 1.7 kilogram. For PFAS, this is actually a bit, it's a lot. This is the vertical profile, so this is the vertical direction. You generally see a bit more higher concentration on the surface, and they actually diffuse into the concrete pad. So this one is probably about 18 centimeter thick, but then when they drill it, they can only drill up to like 12 before the concrete kind of break into pieces, and they were able to measure all the way down as far as they can go. We also did a study. So this is a concrete core we got from Canadian force base, a military base, and this is just like an image of the concrete, the concrete pads. So we get 4 cores, not as many as the Australian studies. So we also measured their concentration. So right now, this is from left to right is the depth of these cores. Again, you see that they tend to have more higher concentration on the surface. The concentration drops when they go deeper, but there are some cores, on the bottom, you're also gonna see a bit higher concentration. This is probably the places where the concrete pads actually intact, they actually interact with groundwater, right? So if the groundwater contaminated, and this contamination can be also soaked up from the bottom, not just only from the top. And we actually found that for Australian study, they saw PFOS is the most dominant one, but for us, it's a slightly different chemical. So this is more like a DuPont chemical, very similar structure as PFOS. For us, we're looking at structure, we can tell which manufacturer made what chemicals. Again, so this has been confirmed. So a couple years ago, this is U.S. Department of Defense environmental program called CERDUP. They have a program to looking at PFAS contamination in concrete. So my team is one of the one getting a grant from the U.S. and then work with 2 consulting firms. So for us, our goal is really to understand contamination of intact concrete, right? So when you have crack, of course, liquid is going to go in, it's going to contaminate inside. But if there's no crack, can these chemicals, they're a bit large in size, can they just kind of diffuse into concrete in the same way as chloride, right? Chloride is much smaller, it's 0.18 nanometer, but PFOS is 7 times bigger. Can this larger molecule get into concrete? Because we actually don't have a lot of experience in dealing with in general contamination of concrete by a large number of molecules. So we did these lab studies. So we have to do it in a controlled fashion because in the labs, in the field example, there's years of exposure and there's a rain events, and you cannot really figure out which is which. So we did these lab studies and we created this miniature cores. We make sure their performance is the same as the large concrete cores, but we have to have a miniature setup so that we don't want to create a lot of kind of waste in the lab, right? This is a big jar of HFF. It's like laundry detergent, and we dilute and we put them on a liquid and we put them on the top of concrete. So we just let them stay there for a year. So this is a very long-term study. And then the other one is we simulate field scenarios. So in the field, they do fire training, say weekly or bi-weekly or monthly. So they kind of release these foams into the ground or onto concrete, and they flush it over and they repeat over and over again. So it's more like a repeat wetting and drying cycles. We did the same thing. We just add a small amount, we let it dry, and 1 week later we add more. So we want to see if 2 kind of different exposure, can we get the different results? We also have a flat, we call surface versus chipped surface. Chipped surface means it's mechanically kind of broken. So because that happens right in the field, over time and weathering event and mechanical forces, the concrete surface is actually a bit damaged. We want to see if there's any difference. And then also after 1 year, we start disassemble it because we want to look at not only what's in the liquid, but we want to see what has went into the concrete. So we take it apart and we start drilling into powders. So we have to drill it, and then we drill it and we collect powder. We make it into different sections. So the number you're going to see is actually average of certain depths. So for instance, you have these 1 segment, you actually make it into powder, you grind it up, and you do chemical extraction. You see how much PFAS are stuck in concrete. We also, this is a little bit more, this is just every time you want to measure some chemical in solid, you actually have to use organic solvent to extract, because the machine, most instrument we use can only measure liquid phase. So you really have to do this extraction. So this is just a bit too chemistry heavy here. Just we have to kind of test what methods works to actually extract this chemical out of concrete. So these are some of the results. So one of the setup we have is really a very kind of ideal system that we only have individual PFAS. We make some artificially. We put in there. This is now real firefighting foams. After 1 year, you see the number flat, which is very boring for a study like this. to me, this tells us we actually cannot tell how much PFAS goes into the concrete based on what's left in the liquid phase. And then this is what we're looking at in the core. So this is just looking at solid part. As you can see, we've seen similar graph like this in the field. This is in lab. So this is what very interesting about the PFAS. You can put a lot of in the liquid phase, and then if you lose a little bit, you cannot tell because it's just concentration very high. But some of them do goes into the concrete, which confirmed our field studies, the field observation. Again, here we have called chipped surface, we have flat surface. We actually find that for the chipped surfaces, you see the numbers here is very high. So chipped surface, when the surface is damaged, you do have a much more penetration of these chemicals, which is kind of makes sense, right? What we notice also in the lab study, we also want to do reproducibility, but for concrete, which is not a very homogeneous material, so we can't really say this is replication, we get average number. No, we have to looking at one core at a time. One core at a time, you see some variation, which is expected. And then this is a more realistic study. So this is where the other step, we just put a diluted firefighting foams, the same concentration as you would use for firefighting activities. So here this is our control. That's a flat number, which means this is really to verify the integrity of the system. That's what you should see. If there's no sorbing phase, we should see flat line. But for the other one, these are just flat surface, and this is a group of them because there's so many different of PFAS. So we have an acronym for them. You see that their concentration effort increase with time, which is really odd, right? Because this chemical, if they go into concrete, they're supposed to decrease, not to increase. It looks like we're creating something. There is a very odd event for us. Some chemicals, they decreasing a little bit, or they just flat. But for this one, they just increasing over time, almost like double their concentration by the end of 1 year, which is, very odd. Again, we were looking at this one, actually, the concrete exposed to the real firefighting foams. Inside the concrete, we see them. We also see the same event if the surface is damaged, chipped, you're going to see much more diffusion of PFAS into the concrete. But you see the profile is a little bit different. Right here, I'm just explaining why the chipped surface would have more PFAS in there. Because if you take any concrete courses, you know there is a word called interfacial transition zone, right? Because this is our aggregates, right? They are bind together by this cement. But in the interfaces where the structure is more vulnerable and it's more porous. So when you have chipped surfaces, you expose this kind of path, this kind of porous space into PFAS, but more directly. Therefore, these are create a bit more preferential path for PFAS to go in. But when you have like flat or fresh concrete surfaces, you don't have that phenomenon. It's mostly diffusion and also transport through water. This is a very interesting image. Most study done, we have to extract concrete using liquid solvent, but this is a new technique that actually is a direct imaging technique done by researcher at University of Queensland. So we collaborate them, and this is 4 different PFAS, and then we actually sideways. So on the right is the top surface. Just because this is how they can fit in the slide. So from right to left, you see that surface into deeper down. Right away, you see the bigger molecule C8. You see they're more concentrated on surface. Smaller molecule, they just go much deeper into the concrete. Again, the confirming, yes, they can all go into concrete, given enough time, but smaller molecules, of course, they're gonna diffuse a bit faster. So this confirm the phenomenon, but this is very interesting tools. So because it really, we don't have to extract a concrete, you just cut it, polish it, and put under this instrument, you can see them very well. This is one slide where this is the wet drying cycle. And then there's no liquid phase left. All we see is what's in the concrete. So we actually do the spiking for 24 weeks because we want to kind of able to simulate things happening in the field for years. Why? Some of the firefighting ground, they've been doing firefighting training to 2-3 decades. That's a lot of accumulation. So interesting thing is when we do this wet, fire, dry queue, you see all different chemical, they all their profile on top of one another. You don't see a difference in their migration rate. The reason we think what happens on the left is the normal one, that's just a static water, so chemical goes in by diffusion. But on the right, because you have concrete that will dry for a period of time and you apply water. So basically just like a sponge, right? Once it dry, it's just gonna sorb water. In the sorb water, it's kind of, we call it weak action. So that kind of pulse moment actually make PFAS go into a bit faster. So this is more of the field condition. So we think this kind of dry wetting cycle really accelerate penetration of PFAS into concrete. This is just a little mass balance estimate. So because in different events, when you have a real firefighting foams versus a lab-made one, because real firefighting foam, there's a lot of additive, there's a lot of things in there. We actually have found that a little bit more actually go into concrete for some reason. But for the kind of pure one, it's actually slightly different story. So the percentage of how much PFAS can go into concrete, it depends on what else in the solution, just not only what PFAS out there. This is a little bit chemical extraction. I'm just gonna go through quickly. This is just to verify our methods, how good they are. So some of the chemicals, you can extract them well, no matter what solvent you use, you see very consistent numbers. Some chemical just not extract very well. This is very large molecules. This is what we know, very large chemical, very hard to get them out from solid. And this is where I was, remember there was some odd events. So when we do chemical extraction, we found the same thing. So when we do this kind of recovery test, we expect everything to be around 100%. But again, some chemicals, we see them, they almost disappear during extraction. Some actually were created. They have recovered like almost like over 1,000%, which is unreasonable. So we think what happens is PFAS in general are stable, but there's a lot of structure have a bit more of structure, and some of the structure can hydrolyze. They don't usually hydrolyze easily, but when you put them in contact with concrete, concrete leach out calcium hydroxide, make the solution basic. And when you have a basic environment, some of chemical just hydrolyze and they actually create new chemicals. So why is that important? Because people has now been looking at a lot of chemicals in firefighting foams. These are non-regulated PFAS, but when you have these events, you create a regular chemical like PFOA. So this have a lot of implications. We just did a little bit further and we find out exactly where hydrolysis happens. So I won't go too far. So this actually thinking about chemical extraction only happens, we do chemical extraction only in a matter of a few hours. So hydrolysis happen also in the field. So when you have concrete, a surface in contact with the liquid, that slow leaching of calcium hydroxide can slowly break down some of the PFAS as well. But this happens in a scale of weeks or months. But in the chemical extraction in the lab, if you don't do it carefully and you don't know what's happening, you could artificially create, which can be avoided. But just saying that if there are scenarios that extended contact of this firefighting foam with PFAS, you actually create the regulate PFAS, which is a problem. And the same thing, so this is another group of chemicals, and these are also the things that will be regulated. This one actually, we don't know toxicity, but it's very persistent and the same status as PFOS, but it has our name called FASA. And then again, so we don't know where this one from. For the other scenario, we know exactly where they're from. For the other scenario, you see how many different classes of these PFAS just in one firefighting formulation. It's a very complex composition. So we see increase, but we don't have a consistent trend of which one break down because some actually we just don't quantify them very well. So we don't know where they're from, but we know we can create some problematic ones that during extraction or during extended contact between concrete and firefighting foams. Again, so now we know concrete can be contaminated by PFAS from H2PF. Once they get into concrete, do they come out? The answer is yes, they do come out. So this is an Australian study. So when they found out the concrete contaminated, they did some desorption experiment to see how much PFAS can come back, and they did some modeling. What they found is every time it rains, some comes out, but not very much. Rains again, some more comes out. So these are some number they find out. For that particular concrete pad, I told you earlier that accumulate about 1.5 kilogram of PFAS in total. It will take them 82 years for 90% PFOS to completely leach out. And then the water they contaminate, and they're going to contaminate groundwater every time rains for years to come. So that's the issue, right? If you have, if this particular site want to redeveloped, we really have to check all the sources, and concrete should be a source to look into if they've been exposed to H2PF. So what do we do in the interim, right? Now, it doesn't mean we have to disassemble all the structure. Is there any solution? One solution is to use commercially available sealants, because there are concrete sealers out there, right? These are concrete coated with sealers for different purposes, right? They actually, one study also from Australian group, so they are pretty far ahead. They tested two commercial sealant, a product A and a B. They actually find B works much better. So this is right now is after the concrete coated, they do leaching experiment. You see these green dots are very low, but you see if it's a concrete is unsealed, you see every time rain, you have pulse of PFAS coming out. Product A didn't really work well, but product B works well. So they didn't tell us exactly what sealant these products are, but right now they have active studies also funded by U.S. Department of Defense, the same funding source I got, to really just test out available sealant, so that for certain structure they can put a coolant the sealants, so that structure can be continued used before the end of their surface life, because we don't just want to demolish all these structure out there. Again, so that's pretty much the end of my study. So take home message: concrete is a sink of PFAS from firefighting foams, but in turn is also a source. So what we studied for this study is mainly 3M H2PF. So what kind of concrete are vulnerable? So surface are damaged. Even though there's no big cracks, once the surface damaged, they're more vulnerable. Also, the wetting drying cycle that can accelerate. But we also find the transformation, which should be really closely watched for, because this feel like sometimes we don't know the identity of some we call precursors, but you see new things are being created over time. So the question is how widespread the issue is. I think it's a pretty widespread. The airports, oil refineries, military bases. I think it's the story from Canada, Australia is similar to many other places. And we need solutions, a short-term and long-term solution. Short-term, can we use sealant? Long-term, what do we do with contaminated concrete? And also in the, I think people, a lot of places, even in Hong Kong, I think people actually are switching to PFAS-free firefighting foams. But what about the legacy issues, right? So this is the end. So this is my students back in Canada. These are the funding agencies. So these are publication that's from the lab studies. Thank you very much for your attention. I know I went a bit too long. It's 5:50, but again, these are our QR code to connect with us through different channels. Thank you very much for your attention.
So thank you for Professor Liu, and so let's come to our Q&A session. So dear audience, again, please feel free to just type your questions in the chat box, and yeah, so we will consolidate the question and ask Professor Liu. So we have the first question from Mr. Ho. It say that given that the concrete acts as both a reservoir and a source of PFAS, could you discuss the long-term environmental and implications more?
Okay, so I'll talk about I guess the case I know from Australia, so also from actually from US. So there has been okay, so right now there's a lot of unknown about toxicity, but if there are heavily contaminated lands, the value of the property themselves decrease. So that's happened with Australia. So there are residential areas, they're really close to military bases. And there are farms that are really close to military bases. We're not even talking about the potential health implication for people who use their groundwater or use the surface water for irrigation or for agriculture purpose. But just the simple thing is these land are contaminated, that automatically actually decrease the land value. So that's actually a lot of issues that people right now dealing with. Just the value. If you talk about environmental implications, we don't want these things to kind of leach into groundwater and transport downstream. People living close to these places, they tend to have a little bit elevated level in their drinking water. Again, the health implication, we only know a few of them compounds. Long-term exposure to these ones, there's a little bit higher risk. If you really actually drinking water has a lot, or you have food, or also in the air you have a little PFAS, there's certain type of cancers. I think it's actually kidney cancers, testicle cancers. Also make people tend to have certain kind of I think hypertensions, or not hypertension, it's a hypertension. I should go on to my slide about health implication. So not the best one, but so these are verified health implications of extended exposure to PFAS. So low birth weight in infants, increased cholesterol levels, decreased vaccine response to children. So these have to be verified. And then there's the cancer implication as well. So again, so that's my answer to Mr. Ho's question.
So thank you, Professor Liu. And see if we have some more questions from the audience.
Yeah. So I think Hasing has a, could you show the previous slide? I don't know which slide because I wasn't looking at my slide. I don't know which slide. So I think in the midways. Do you know which slide? I think around 35, 30-ish.
Oh yeah. The what is concrete slide?
Oh, okay. Okay, what is concrete? Okay. Okay, this one. Right.
Yeah.
But yeah, well, I think we all seen these concrete trucks, right? So these concrete trucks, I think you make, so concrete, there's many different type of concretes, right? There's just so many different, depends on the application, depends on the climate, depend on the raw material you have. But basically you mix with water, aggregates of different size and the sand and cement. You mix them up, right? And then you pour into a structure. So this is how concrete and then when they first fresh poured, they're soft, but it usually take about 30 days for they fully hydrated, for them to have the required kind of mechanical property to serve as a structure support, right? You see that in pavement, in the foundation, so many structures. Yeah.
Yeah, so we have one more question from Min Wu. So dear Professor Liu, thanks for sharing. For those PFAS released into concrete, is it possible for them to get back to the environment via air media, cause inhalation risk to human beings?
Oh, yeah, that's a great question. So, okay, for these particular ones we're talking about from firefighting foams. Okay, for firefighting foams, actually, if you have a jar of these firefighting foams, when you open it, they actually have a trace amount of volatile PFAS in there. These are structurally different from the ones I shown you. Those are most of the impurities they use for synthesis. So those the synthesis raw materials actually are a bit more volatile. But then when they make into kind of surfactants into firefighting foams, they're not volatile. So yeah, so the question is, the ones that release back into environment, they have very little inhalation risk to human beings. That being said, if there are places, for instance, there are wastewater treatment plants, right? If there's a wastewater treatment plant handles industrial wastewater, and these PFAS are stable, but some of them goes through transformation for certain, actually, especially DuPont chemical, they call fluorotelomers. Their transformation products actually give trace amount of volatile compounds as well. But for human, I would be most concerned about the PFAS in carpets, in paints. We actually don't know how much residues in there, especially the volatile raw material. But I know when I did my study in the laboratory, we actually can detect volatile PFAS in the air. So if you have kind of stain-resistant carpets, if you know they are PFAS, made PFAS, probably early time when you use those ones, there are probably trace amount of them released into air. So that's how, consumer actually get exposed. Like the new product tend to have a bit more older product, no. We get them from water, from food, from air. So, that's how they get into our body. We don't use firefighting foams, and we don't usually get onto the basis of there's concentrated stuff. So we don't get exposed in that scenario, but we do get exposed through consumer products. Hope that answers your question.
Yeah. Thank you, Professor Liu. So this maybe a kind of question I'm asking: is it possible to get the PowerPoint for the seminar, and for the recording? And I'm afraid we cannot provide.
Okay.
How about the
So
PowerPoint for?
yeah, so I think there's a few slides that has not been published. I will get approval from my partner, the collaborator from Tetra Tech and CDM Smith, two US companies. Or if they don't want me to release data, because one is promised to publish two studies. Most of the data has been published. There's one source of data I haven't published. One option is I delete those slides and share with you now, or in a couple months when everything's published, I can share the full slides in its entirety. So yeah.
Okay, yeah. So, so if Professor can give us the PowerPoint or the edited PowerPoint, then maybe we will send
Okay.
the PowerPoint to the audience via emails. Yeah,
Sure,
and
sure, I'll do
maybe
that.
yeah,
Yeah.
maybe it is the last question from Kun Ho Lao. So, what is the difference between normal concrete and self-compacting concrete? Okay,
Oh, actually, I don't know. I maybe there are some engineers on
yeah, this
who
is a
work.
more engineering questions.
Yeah.
Yeah.
Well, I should have known. I've taken concrete course years ago, 20 years ago when I was a student. I
Yeah,
don't remember now.
it's
Yeah, yeah.
it's fine. Yeah, I think the answer can be searchable. Yeah.
Yeah,
So
yeah.
yeah, so thank you, Professor Neil, again, and thank you all the audience. And for the certificates or for the PowerPoint, if Professor Neil provide later, then we will send to you all via email in due course. So thanks again, Professor Neil, and thanks again for the audience. So see you all soon, and thank you.
Okay.
And yeah,
Yeah.
yeah,
Thank you,
and
Daniel.
yeah.
Feel free to reach out to me if you're interested and want to know more, or you have some projects you are concerned about PFAS. I'm happy to chat. Yeah.
Yeah, yeah. So thank you very much, Professor Neil, and yeah, see you all, and bye bye.
Okay. Bye.